Let's look at how the depth varying velocity solution for flow in an Ekman layer satisfies the Ekman balance. And for that, I've already written the U and V that are the Ekman spiral. So U is U naught times e to the az cosine az minus pi over 4. And V is almost the same, except it's a sine instead of a cosine. And the A is defined as pi divided by HE, where HE is the Ekman depth, and that's given below. HE is pi times the square root of 2az divided by F. Az is the vertical eddy viscosity, and F is the Coriolis parameter. U naught is square root of 2 times pi times the wind stress divided by rho, which is the water density, FHE. And this solution for the Ekman spiral works for winds in the x direction. The x momentum balance is a balance between Coriolis acceleration, that's on the left-hand side, and frictional force per unit mass, that's on the right-hand side. So we have negative FV equals positive ddz of az du dz. So now what we have to do is we have to substitute in our expression for V and our expression for U, but then of course we're going to have to take derivatives. So on the left-hand side, we have negative F times U naught e to the az sine az minus pi over 4. And that equals, on the right-hand side, ddz of everything else in the square brackets. That's az times ddz of everything inside the smaller square brackets, which is u. So that's u naught eaz cosine az minus pi over 4. The next step is taking du dz. We have to take ddz of everything inside that smaller square brackets. And remember, we have to apply the product rule. So we have to take the derivative of e to the az, as well as the derivative of cosine. So in doing that, we come up with a u naught e to the az times cosine minus a u naught e to the az times sine. The next step is taking the second vertical derivative. We're going to consider az to be constant with respect to depth, so it can come outside of the vertical derivative, but we still have to take the ddz of everything else in the brackets. There were two terms in the du dz term. Now that we apply the product rule to each of those terms as we take the derivative, we end up with 4 terms. The two cosines are underlined in yellow. Everything's the same about these terms except for the sign. One's positive and one's negative. The two sine terms are underlined in green. These are exactly the same, even both having a negative sign. The cosine terms inside the square brackets cancel out. The sine terms are left, but now there's a coefficient of 2, because we added 1 plus 1 of them. So on the right-hand side, now we have negative 2 az a squared u naught e to the az sine az minus pi over 4. And on the left-hand side, we still have negative f u naught e to the az sine az minus pi over 4. Everything underlined in red on both sides is the same, so we can cross that out. And then we can change the negative signs to positive on both sides. What we're left with is f equals 2az a squared. Now, let's substitute in the definition for a squared, which is pi squared over he squared. That leaves us with 2az pi squared over he squared on the right-hand side. The next step is entering in the definition of the Ekman depth, he. At that point, we have 2az pi squared, in parentheses, times f, divided by pi squared 2az, in parentheses. The quantities in parentheses are actually the same, so they cancel out too. So we have f equals f. And that's true. If we want to take it one more step, we can divide through by f and get 1 equals 1, which is an identity. So we've shown that the Ekman layer velocity solution, u and v, satisfy the x momentum balance for Ekman dynamics, which is the Coriolis acceleration equals the frictional force per unit mass. We can pursue the same methods to show that the U and V solution also satisfy the Y momentum balance for Ekman dynamics. But I'll leave that to you to do on your own. Of course, if you want to.